Hey, welcome. Have you ever stopped to think about how an app on your phone can search through millions of items in just a split second? It feels like magic, right? But it's not. It's all about having the right digital toolbox. Today, we're going to pop that toolbox open to really understand algorithms and data structures. And it all comes down to one simple question. So, imagine you're a programmer. You've got a problem to solve. You have this whole set of tools you could use. But here's the thing. Just like a carpenter isn't going to use a hammer to saw a board, a programmer has to pick the right digital tool for the job. And getting that choice right, well, that's the difference between an app that's snappy and feels amazing to use and one that's just clunky, slow, and frustrating. Let's make it even simpler. Think about it like this. You need to find one single fact from a giant book. Now, you could read the entire book, cover to cover, until you find it. And hey, that's one way to solve the problem. But you could also just flip to the index, find the exact page, and get your answer in seconds. Both methods get you there, but one is obviously way, way smarter. In the world of programming, finding that smarter way is all about choosing the right algorithm. Okay, but in this digital world, how do we even measure smarter? Before we start grabbing tools from the toolbox, we need to know how to read their labels. And for programmers, the most important label, the one that tells you about performance, is something called time complexity. So, time complexity. It sounds kind of formal, I know, but it's really just a way to measure how an algorithm's runtime scales up. You see that letter N on the slide? All that means is the number of items we're dealing with. So if we go from sorting, say, 10 photos to 10 million photos, time complexity is what tells us how much more work that algorithm is going to have to do. The key thing to remember is it's not about the exact seconds, but about how the effort grows as that N gets bigger and bigger. And we measure this growth using a pretty simple rating system called Big O notation. Let's go back to our book analogy. Reading the whole book to find that one little fact, that's what we'd call an O of N algorithm. The work you have to do grows directly with the number of pages, N. But using the index, that's O of log N. See, every time you check the index, you're basically cutting the problem in half. This whole divide and conquer thing is incredibly powerful, and that's why it gets that excellent rating. It barely slows down at all, even if the book is massive. All right, so let's finally open this toolbox. First up are the data structures. And the best way to think about these is they're different kinds of digital filing cabinets. Each one has its own unique system for organizing your information. Our first filing cabinet is the hash table, and honestly, it's pretty much magic. Instead of you having to search through a bunch of drawers, it uses this really clever trick. You give it a piece of data, we call it a key, maybe a person's name. It runs that key through a special formula, a hash, that instantly tells it the exact spot where the information you want is stored.
No searching needed.
At all. And that is its superpower, pure speed. Because it doesn't have to search, a hash table gives you what feels like instant access to your data. It is the absolute best tool when you need to find something in the blink of an eye. So when would you actually use this? Well, think about the contacts list on your phone. You type a name, that's the key, and instantly the phone number pops up. That's the value. Yep, that's a hash table working for you. It's like a digital dictionary, perfect for any this equals that kind of situation. Next up, we've got a totally different kind of cabinet, the binary search tree, or BST for short. Now, this one is absolutely obsessed with keeping things in order. It lives by one simple rule. For any piece of data, everything to its left has to be smaller, and everything to its right has to be larger. This structure means the whole thing stays perfectly sorted, all the time, automatically. This built-in order makes a BST act just like a perfectly organized physical file cabinet. Since everything's always sorted, it's fantastic for grabbing not just a single item, but a whole range of items, like, say, all the names from L to M. This kind of efficiency is exactly why it's a core part of the internet's domain name system, helping you find one website out of billions. Okay, our last organizer is called the heap. Now, don't worry about the technical definition on the slide. All you really need to know is its one golden rule. The most important item, whether that's the biggest or the smallest, is always sitting right there at the top. Every single time you add or remove something, the heap just instantly reorganizes itself to make sure that top spot is correct. So why is that so useful? Well, picture a live gaming leaderboard. You've got scores changing constantly, players are joining and leaving, but you always need to know right now who's in first place. A heap is absolutely perfect for this, always keeping the top K players right there at your fingertips, ready to go. So we've got our filing cabinets, our data structures, for keeping all our information nice and organized. But what about the tools that actually do the work? Well, for that, we need to grab our power tools, the algorithms. These are the step-by-step recipes that do the sorting, the searching, and the building with our organized data. So let's look at a classic power tool team-up. First, you've got Quicksort. Its whole job is to take a completely jumbled mess of data and just whip it into perfect order. Then, once Quicksort's done its thing, you can bring out its partner, binary search, which is a super efficient finder that only works on data that's already sorted. The real magic behind binary search is that divide and conquer strategy we talked about. Remember that excellent O of log n rating? This is it in action. It jumps right to the middle of a sorted list and just asks one question: is what I'm looking for bigger or smaller? And based on that answer, it instantly throws away half the list. It just keeps doing that, chopping the problem in half over and over and over until it zeroes right in on the answer. It's incredibly fast. So how do we put all of this together? Look, being a great developer isn't just about knowing what these tools are. It's about being able to look at a problem and know exactly which tool, or maybe even which combination of tools to grab from that toolbox. Let's just do a quick recap with this summary table. Think of it as your cheat sheet. You need instant lookups, like a phone book. You're going to grab a hash table. You need to keep your data sorted so you can search for ranges, like with website names. That's a job for a binary search tree. You need to always know who's number one on a live leaderboard. A heap is your go-to tool. Got a big, messy list? You use Quicksort to get it in order. And then, once it's sorted, you need to find one thing in it. You unleash the power of binary search. It's all about the right tool for the right job. You know, these tools we've talked about built the entire digital world we live in today. But our problems are getting so much more complex, right? We've got AI, we've got global scale data, and we've got challenges we can't even imagine yet. And that leaves us with a really fascinating question to think about. What new tools will the next generation of builders need to invent for the toolbox of tomorrow?